Today we're going to be demonstrating how to jump a car's battery, and we're going to examine the circuit that is created between the two batteries with the jumper cables. And we're going to see how the current flows from one battery to another and then gives this battery charge so the car can start. To begin setting up the circuit, you take the red positive cable and you will connect that to the positive terminal of the charged battery. So you just clamp it on to the exposed metal part. Terminal. Then you will attach the positive cable to the end of the battery that needs charging, the positive terminal of that one. So you just keep that right there. Thirdly, you do the negative cable to the negative terminal of the charged battery. And the most important step is you take the other end of the negative cable and you attach it to a ground metal that is not the negative terminal of the battery, because we want to reduce the risk of creating a spark and the battery exploding. So you can attach that to any unpainted metal, such as the car body. That's plastic. So where's metal? You know what? There we go. That's it. Now our circuit is complete. We're going to examine how exactly that works and how the transfer of current is going to come from this battery to this one.
After connecting each of the jumper cables to the respective terminals, there are 3 different types of currents that are going on between the active car and the dead car. The first type of current going on is the electric current. The electric current is the flow of electrons and current from the positive terminal of the active car into the negative terminal of the dead car. The second type of current that's going on is electron current, and that's basically the opposite of the electric current, because it's going from the negative terminal of the active car to the positive terminal of the dead car. And finally, the third and final type of current going on is the hydrogen ion current, which is quintessentially the same direction as the electric current, due to the hydrogen ion acting as a catalyst to bond with the sulfuric acid inside to cause a jump start.
Alright, so now we want to speak about an actual problem that you might get with batteries, which is very common. So as you can see under Emma's car, the goddamn nasty terminal is full of corrosion right here. You see that? Corrosion, bad. So what actually causes corrosion is the hydrogen gas released by the battery that mixes with the atmosphere in the air, and then it causes chemical reactions and it settles right here in the terminal. So very typically you can just walk into a auto shop or somewhere and you can get some corrosive acid to clean it off, and then boom, brand is new. But for now we'll leave it. So the problem with corrosion is that when you have a terminal and you hook it up, it creates a false contact. So meaning that corrosion acts sort of like an insulator, which prevents your terminal from actually being hooked onto your battery.
Boom.
Alright, so now that we've examined a car circuit, we're going to apply it in a real world situation. So we have this question: when a 12-volt car battery runs a single 30-watt headlight, how many electrons pass through it each second? Alright, so to find the number of electrons, we must first find the charge moved in 1 second. So 1.00 s, and we know that the charges moved is related to the voltage and the energy. So we use the equation U equals Q delta V. Alright, so from here we solve for Q, so it'll be U over V equals Q, and then we know that U equals the 30 watts. 30 watts would be equal to 30 joules, and since it's losing energy, it'll be negative 30. So negative 30 joules per second, but we're already figuring it out for how much we're losing in 1 second. And we divide that by the volts, 12 volts. Is Q, and then Q equals negative 2.5. So to find the number of electrons, we take this Q here and we divide it by the charge per electron. So we'll take Q over the charge, which is negative 1.6 times 10, negative 19 coulombs per electron. And we know Q, we just figured it out here. So we can plug that in, negative 2.5, and then coulombs cancel, and then we're left. We are left with 1.56 times 10 to the 19 electrons.
Alright, so this time we're going to be taking another look at a different problem. So, suppose you have a 12-volt motorcycle battery that can move 5,000 coulombs of charge, and a 12-volt car battery that can move 60,000 coulombs of charge. How much energy does each deliver? Alright, so for this one, we're going to separate the car and the motorcycle to different steps. So first, we'll take out the motorcycle motor. Alright, so now we know that the voltage here is 12 volts. And that the charge is 5,000 coulombs. An important relationship to notice here is that the electric potential energy difference is equal to the charge times the potential difference. So now, solving for our potential electric energy, we just plug in values. So we get that 5,000 coulombs times your 12 volts gives you, I forgot the number. Alright, so then 5,000 coulombs from 12 volts equals to 60,000 joules of energy. So that's for the motorcycle right there. Now we'll take a look at the car over here. They give us that their voltage is again 12 volts, and that the charge this time is 60,000 coulombs. And again, we're going to use the exact same relationship: electric potential energy difference equal to the charge times the potential difference. And again, just substituting our values, we get 12 volts times 60,000 coulombs equals to
720,000.
720,000 joules of energy.